Okay, this is another example. Here we have a box containing a high fidelity 8-track tape. You probably may have seen 8-track tapes. They were in cars in the 70s, so perhaps not, but your parents would definitely know what they are. Basically a tape that would wind itself around and you could play any song on it by clicking on it. So unlike a cassette where you had to fast forward or rewind. Anyway, very obsolete by today's standards. So better you're born now than then. So anyway, so here we have our 8-track cassette in a box and we drop it. Now we're told that the box hits the ground at 4 meters per second. So that's its V final. Upon impact, the foam inside compresses 15 millimeters. So we're treating the foam somewhat like a spring, where we have a negative kx as the acceleration. So a negative being that the acceleration is, of course, going to go that way. The box is going to hit, but it's going to be accelerated back up. So we want to calculate what is the actual acceleration. So what is A? That's what we're looking for. So it doesn't seem like we have a lot of information, but let's look at what we do have. So in this case, we can say that A is a function of position, or x. So with that, we can say that we go back to our old equation that we like. A dx equals V dV. All right. Now, we can just leave it just like this because A is in form of x. So if we set up our integral, what are we going to have? We're going to have V naught to V final, V dV. Sorry, I moved this to the other side. And that's going to equal x naught to x of A dx. So actually, instead of writing A in there, I am going to just write the direct equation. So minus kx, which we know we could write the A dx. So we're going to substitute that in. So minus kx dx. There we have it. So after we set that up, we can look at it and say, well, what do we know? Well, we can, if we integrate this, the V dV, then we get V final squared over 2 minus V initial squared over 2. And that is going to equal just what? Negative 1/2 k x squared. And so we know that it's going to be x, and what we'll do is we'll say this is x final because x initial we're going to assume is 0, okay? Because we know it compresses 15. And that's the whole compression goes from, if we think about it, from 0 here down to the final, which is 0.015 meter, okay? So what do we know? We know V final is 0 because it stops. So even though it hits at 4 meters per second, the final velocity of the whole object is 0 when it comes to rest. So this comes down to 0 minus, it starts at 4, so that's going to be what? 16, 4 squared over 2, and that's going to equal minus 1/2 times k. We don't know what k is, but we do know the x final. That's going to be this distance, 15. So 0.015 squared. And now we can solve for k. So once we get k, then we can come back up here because we know x. If we know k, we know acceleration. So it seems circular, but it's not, because we're saying how much is k based on how fast it was going and how much did it compress, because that's going to have to tell you the distance moved based on the velocity. So if we solve for this, we have 8 equals negative 8, sorry, equals negative 1/2 k times 0.015 squared. So the units are, of course, on both sides end up meter squared per second squared. And so the x side ends up being meter squared second squared. So only the meter squared cancels. So what k has to be in order to give these units the units correctly, right? Because you have meters per second for velocity squared. Over here, you have the distance squared, that's your meters, and your k below. So your k unit ends up being k equals 71,111 s to the minus 2. So that's the unit on S, so that the units are consistent. Now, I know we don't talk a lot about units. We kind of assume they're going to work out, but it is good to keep track of them on certain problems so that you understand where they're going, especially on something like this. So now we have K, and we're pretty much done because now we know that acceleration maximum is going to be equal to this negative K times X, or negative 71,111 times 0.015. And so the units work out because this is 1/2 squared and this is meters. So we get a final answer of about 1,067. And we can leave it in the negative because of the direction. 1,067 meters per second squared. So put that in perspective. So how many G's is that? That's about 108 G's. So figure if you're flying in a plane, let's say you're in a fighter plane, you're only going to feel, well, ideally you don't, I think if you feel over about 7 or 8 G's, you're going to black out, even less, depends on the person. And obviously those guys are in really good shape, but your average person will be well dead long below you ever reach 108 G's. So the point of the moral of the story is you don't want to be dropped in a cassette track box and end up hitting the ground at 4 meters per second, or so they say. All right, I hope that helped. Just another example, but again, notice the AX, DX, VDV comes in to help us again. So I will add this to the rest of the examples, and I'll see you in class. Thank you.